Okay, so the main issue this week is exam 2 is on Friday. And so, yeah, let's figure out what material is going to be on there and what practice problems. So it is Friday, what's that, the 28th?
Yeah.
Okay, so last time we went up to 14, is that right? And so, was uniaxial loading on there?
Yeah.
It was. Okay.
We just set up like different. Our number 14 was like a structure problem.
Oh, really? Oh, this is the wrong set. Okay. These are old. All right, sorry about that. Okay. Okay, so you had that one truss problem. Okay, so there's going to be internal load stuff. So 15, 16, 17, and that's the end of the first set. So all the way to the end of the first set. And I guess that's all there's going to be at this point. Yeah. So just until the end of the first set of practice problems.
We're not going to have anything on stresses from bending moments.
Right, because I have all those problems also have shears in them. So all the stuff that we're doing right now is sort of set up for the next exam, for exam 3. So practice problems through the end of the first set, and the stuff in lecture through internal loads. Okay, and so the exam is going to be problems with internal loads, and the lecture quiz is going to be on, the lecture material talking about internal loads. I'd be happy today or Wednesday to answer as many questions about practice problems and stuff like that as you'd like. First, any questions about the test itself? Okay, and then,
19.
okay, and that's the one that might be,
Yeah, added like a force. Keep working the way there, and then we'll-
shoot. Do you have those with you? That'd be easier than me looking this up again. Okay, so 19, and then okay, so you have a cantilever beam. That means you have a reaction force and a couple. And 2 triangular loads. One thing that's interesting about this is, well, helpful about this, is think of those 2 right triangles. I guess let me draw the problem here first. So you have this cantilever beam, and then you have 2 triangular distributed loads. We're ignoring the weight. Each of these, the top point is 40,000 newtons per meter. And the total length is 1 meter, so each of these is half a meter. So what are you doing when you, once you choose a body to isolate, and the first step is we're going to isolate the whole beam. So now at this point I've chosen this body to isolate. Now the next thing we have to do is represent the distributed load as a point force. Well, what are you really doing when you represent a distributed load as a point force? What kind of calculation is that? And what you're trying to do is find the centroid of a shape, right? So we're trying to find, and we don't care right now about vertically where the centroid is. We only care left to right where the centroid is. Well, notice that this shape has a line of symmetry through there. Okay? And so for the first part of this problem, where you're just trying to figure out the point force representing these two triangular distributed loads, the centroid has to be on this dotted line. And so you can just skip the step of calculating the centroid and just go right to calculating the sum of the areas of these two things. You know that the point force is going to act at the middle of the beam. Does that make sense? Otherwise, if you don't do that, it's easier to represent this as two different distributed loads than to represent it as a single one and calculate the centroid of the single one. You could do that too, but it's easier to just say, okay, the centroid of this one is going to be here, the centroid of this one is going to be here, calculate what this point force is, calculate what this point force is. Okay, so what's the area of each of these two triangles? You have, so the area of one of these triangles is the height, 40,000, times the width, 0.5, divided by 2, so 10,000. That's for each one. And so we have a point force here of 20,000. And then in the solutions, there's another force, is that right?
Hmm. Before, the way you have it, 25,000 Newton force going up.
Okay. Yeah, I took that out because I remember that now. So I took that out because it meant extra cuts, and it just made that problem really, really long to do. It's still pretty long.
Thank you.
Yeah. You want me to go through it?
Yeah.
Or do you guys want to go through it together?
No.
Me.
Go ahead.
Okay. We're going to finish that. I like that enthusiasm. Okay, so the first thing we're going to do is figure out the reactions. Newton's second law says this plus this is equal to zeros. And so that reaction force is just 0, 20,000. And then the rotational equation calculated about the left says MR, the 20,000 Newton force, if our about point is at the left, this would make it rotate clockwise about a hinge there. So that's going to be minus 10,000 is equal to 0. And so MR is equal to positive 10,000. And what are the units on this? Newton meters, yep. And here this would be newtons. All right, so the next thing we have to do, we have the external loads. So we have 20,000 up and 10,000 Newton meters that way. And then we have those two distributed loads. And now we have to do the cuts. How many cuts are we going to have to do? 2, unless you have a function in mind, a single function in mind that represents these two triangles. I don't. And you don't either. Okay, I'll just come out and say it. Okay, so we're going to do a cut, but the absolute value function. Well, since the way you do math with absolute value functions is to break it up into 2 pointwise functions, that's true, but it wouldn't help you. So you got to do 2 cuts. So one cut has the right end between 0 and 0.5, and the other one has the right end between 0.5 and 1. So cut 1, x is going to fall between 0 and 0.5. you have the 20,000 Newton force and the 10,000 Newton meter couple. And then you have the most hated of all things, really. You have a distributed load that is not hard to deal with if you go all the way out to here, because then it's a triangle. But notice that our piece doesn't have, it's missing the end. And so our piece is a trapezoid, okay? So what do we know about this? Well, at this end, we know this is 40,000. But what the hell is this one? Okay, so that's the problem. And so you could do it a couple ways. You could come up with a function that represents this and integrate. Or you could break it up into a triangle and a rectangle. Okay? And just do it as two different distributed loads. That's probably the easier way, so let's do it that way. So let me first just to clarify, like, so when these triangular distributed loads, like what makes this one tricky? What's the problem here? So there's something that should come up in these, for some of these triangular distributed load problems, that's just saying, okay, this is going to take a while. What is it? What's the thing that makes it difficult? That makes us have to represent it as a trapezoid instead of as a triangle? The key is that your cuts are going from the wall of the triangle out to somewhere in the direction of the point of the triangle. Okay? Like, notice if we had something like this, okay, and we cut halfway, or, cut somewhere out here, we're still missing all this triangle, right? But because the triangle is facing in this direction, the piece we have left is still a triangle. You see, like we're cutting off the wall side of the triangle. It's when you cut off the point side of the triangle that it changes the shape, okay? So these are going to be tricky. If you only have one triangular distributed load, you can get around that by doing your cuts from the right end, although I always just do them from the left anyways, but you can get around it by doing it from the right. But in this case, there's no way to get around it because you have a triangle facing this way no matter which way you cut. Okay. So the short answer is, as long as you're cutting from the left, any triangle where the wall of the triangle is on the left and the point is on the right is going to be a nuisance. You're going to have to deal with this trapezoid thing. It is always fairly easy because you're just integrating the integrating a line. Finding the centroid, finding the centroid of it is the trickier part, I guess. It's still not horrible, but if we break it up into a triangle and a rectangle, we can do it without any integration. People seem to generally like that better, so let's do it that way. Okay, so what's the linear function that represents the height of this triangular distributed load? Yes. So this function is, you can think of it as y is equal to minus 80,000 x plus 40,000. And if that pops into your head and you're not sure that it's right, just check it against these 2 points. You know it's linear, so if it goes through this point and this point at the end of the triangle, you know that it's the right function. So when x is equal to 0, you have 40,000. That part works. When x is equal to 0.5, you have 0, so that point works. And so this is the right function. Okay. I didn't finish all these, so remember that we have these internal loads to deal with. But okay, so what that says is if the function is y equals negative 80,000 x plus 40,000, and this point here is represented by the variable x, then what's the value at this point? Well, it's just the function. Okay? So you could redraw this as, well, okay, so there's the beam. This point is 40,000. This point is minus 80,000 x plus 40,000. And so there are two things we need to know. We need to know the height of the rectangle, and we need to know the height of the triangle on top of it. What's the height of the triangle? Or how would you calculate that? Well, it's just going to be this height minus this height, right? So what's 40,000 minus negative 80,000 plus 40,000? It's just positive 80,000 x. And what's the height of the rectangle? Yeah, rectangle. Exactly. Yep, good. Minus 80,000 x plus 40,000. So the area of the triangle is the height times the width divided by 2. So 40,000 x squared. Okay. So that is going to be the point force representing that triangular distributed load. Any questions about that yet? And then for the area of the rectangle, that's going to be negative 80,000 x plus 40,000 times x. And so that's equal to minus 80,000 x squared plus 40,000 x. And then, so these give us the magnitude of those point forces. What are the centroids of those two shapes? So where are the point forces going to act? Where's the triangular one going to act? Yep, a third of, so this whole thing is x, and so it's going to be x over 3, And then the rectangular one is just going to act at x over 2 right in the middle. So I can rewrite this now as a point force over here of, so this is the triangle, 40,000 x squared, and a force here of negative 80,000 x squared plus 40,000 x. Then we have the force at the wall. That's, what was that, 20,000 up? And then the couple of 10,000 counterclockwise. And then, yeah.
One side for a triangle is one side location of the path. For the triangle one is on the heart. Which location we taking for the remaining diagram for the force?
This?
Yeah.
Both of them. See, I haven't done it as, so you could do it as a, you could figure out the centroid of this trapezoidal shape, but that's unnecessary work. So just continue to treat it as two different distributed loads, a triangular one with this magnitude and a rectangular one of this. So this is the triangle and this is the rectangle, okay? All right. Oops. Okay, so just move this over to the next page now. So you have room in your notes. So Newton's second law says 0, 20,000 plus 0, negative 40,000 x squared plus 0. Now, these signs can get a little confusing sometimes, but this is a downward force with this magnitude, which means as a vector, we're going to treat it as in the y direction, the opposite of this. So we have 0 and then positive 80,000 x squared minus 40,000 x. You can, it's easy to get sort of talk yourself backwards on this kind of stuff, but just think of it this way. This arrow is indicating a unit vector down, right? And the magnitude is minus 80,000 x squared plus 40,000 x, okay? So as a vector, what's a unit vector pointing down? It's 0, negative 1, right? And so what we have is negative 80,000 x squared plus 40,000 x times the unit vector 0, negative 1. And this is what it gives you. So t negative v. And I think that's everything. So t is equal to 0. V is equal to, did I make a mistake? Oh, I didn't think so. 40,000 x squared minus 40,000 x plus 20,000. And then the rotational equation. So first we have this 40,000 x squared force with a moment arm of x over 3. So that is 40,000. So that's 13,333 x to the third. And would that produce a clockwise or a counterclockwise moment? Clockwise, so negative. So we have negative 13,333 x to the third. Any questions about that one? And then we have another clockwise moment that's this magnitude times x over 2. So that is, minus negative 40,000 x to the third plus 20,000 x squared. Sorry. Any questions about that one? And then plus m minus vx. And now you have a whole bunch of sort of messy algebra to do because you have this messy expression for v. What? Oh, yeah. Thank you. Got that. So plus 10,000. That's the couple. Plus m minus vx is equal to 0. And those couples are sneaky too, because if you miss that, you won't catch it from the derivative, you know, so it'll just sneak by your radar. All right, so this simplifies to be m is equal to positive 13,333 x to the third plus 40,000 x to the third minus 20,000 x squared minus 10,000 plus Vx so these multiply and then I switch. Yep, thank you. And so this is wrong too. Okay, so this should be minus, this should be plus. Okay. And so that is minus 26,667 x to the third. Oh, are they? Thank you. Okay, so positive 13,333 x to the third minus 40,000 x to the third plus 20,000 x squared minus 10,000, and now plus 40,000 x to the third minus 40,000 x squared plus 20,000 x. All right, so let's group some of these. So here are the x cubeds. 1, 2, 3. And yep, those two cancel. And then here are the squares, here and here. And we're left with m equal to positive 13,333 x to the third minus 20,000 x squared plus 20,000 x minus 10,000. And if you wanted to plot this function, I mean, I wouldn't ask you to plot this on a test. If you wanted to plot it, you could do it in Excel or, you know, MATLAB or something. So are we done if you don't have to graph it? No, because we still have the other cut to do. But the other cut is easier. So remember, this is all just still that first cut. So now cut 2. What are the allowable x values for cut 2? .5 to 1. All right, so this cut looks something like this. We have the entire triangular distributed load on the left. That's good. That's going to make that a lot easier to work with. It has a height of 40,000 newtons per meter. We have this upward reaction force of 20,000. We have a couple of 10,000. And now over here we have this incomplete triangle. The good news is, since the point of the triangle is on the left side, it's still a triangle. We don't have to do that trapezoid thing. The moderately bad news is that we don't know what the value of this is. But if we come up with an expression for that function, the function like this line, that'll give us the value here. So what is this function? 80,000, let's try it. So 80,000 x minus 40,000. So when x is equal to 0.5, you'd have positive 40,000 minus 40,000, so you get the value you want there. And then when x is equal to 1, you'd have positive 40,000, so it works there. Okay, so this is the height of that distributed load. Then T, V, and M. So now to treat those as point forces, you have the 20,000 there, the couple. The point force here, what's the magnitude of that point force? Yeah, it's 40,000 times 0.5 divided by 2, so 10,000. And then we have this triangle that is 80,000 x minus, so the area of this triangle is 80,000 x minus 40,000. And what's the width of this triangle? X minus 0.5. You can think of it as like, well, x is going to be something bigger than, think of it for x equals 1. You should get 0.5, you know. So 1 minus 0.5. And then divide by 2. You got to FOIL that out. So 80,000 x squared minus 40,000 x minus 40,000 x plus 20,000 all divided by 2. And so you get 40,000 x squared minus 40,000 x plus 10,000. And so this is 40,000 x squared minus 40,000 x plus 10,000. And then the internal loads. So Newton's second law says 0, 20,000 plus 0, negative 40,000 x squared plus 40,000 x minus 10,000 plus 0, negative 10,000, and then plus t minus v is equal to zeros. So t is still equal to 0. V is equal to positive 10,000. Oh, and that's positive 10,000. That's going to cancel with this 10,000. So we just have minus 40,000 x squared plus 40,000 x. Everyone agree with that? Okay, and what were the magnitudes of these? This one was 10,000. This one was, let's see. Thanks. 40,000 x squared minus, okay, plus, is this 10,000? Okay. All right, so the rotational equation says positive 10,000, that's the couple. And then what's the moment produced here? So that, yeah, right, that's going, yeah, one page.
On that shear force, what happened to the 20,000?
On the shear force, the 20th, this one?
Yeah.
This one and this one added together to give 10,000 acting up. And then that canceled with the 10,000 acting down over here. So positive 10,000. And then this one, what's the location of that one? It's a third of 1/2. So that should be 1,666, right? And that's clockwise, so 1,667. Yeah. And then what's the location of this one? That one's sort of a mess, but it is, so the location, you can think of it as, yeah, that one's a mess.
That's 2 b over 3 plus 0.5, isn't it?
What?
Isn't it 0.5 plus 2 b over 3? For that.
It's 0.5 plus 2x over 3, right? Yeah.
Because you start from the left.
Yeah.
If you start from the left.
X is the whole length, so you want the length of your small triangle on the right is x minus 0.5. So you want 2/3 of x minus 0.5.
Right.
Plus
That's right.
0.5.
That's right. That's right. Okay, so it's going to produce a clockwise moment, so it's negative all of this minus 40,000 x plus 10,000. And the moment arm is, so we can all agree that it's more than 0.5. And then the additional part is 2/3 of x minus 0.5, right? And then plus m minus bx is equal to 0. I'm going to try to put one on with a little more algebra than this. Because there's no more important test of an engineer than how good they are at foiling long stuff out.
You should give us one that's the bent is already bent. We have to do it.
Yeah. Well, we can't do that. But I can tell you how to do that if you ever want to know. Come by my office.
Would you consider how do you get the x towards the x minus 0?
Which one?
The location for on the left.
This?
0.5 plus 4%.
Yeah, so it's, okay, so the triangle is like this, right? And this distance is x minus 0.5. And so it's 0.5 to get here plus 2/3 of the way along x minus 0.5. Okay, well, we don't have time to multiply that out, thank God. But, I mean, right, on a test, I'm going to do everything I can to make algebra not the thing you spend the most time on, you know. The kind of thing that I can do, like some of the things that are, you know, options that are at my disposal, is make you do free body diagrams but not do the calculations, you know. Or obviously, like, no, I'm not gonna have you do one of these with 2 triangular distributed loads, but I could make you understand how to do one of those trapezoidal things, like say you have to work from the left on a triangular distributed load, you know what I mean? So just be sure you understand how to do those trapezoidal ones. But no, I definitely wouldn't make you do one this long. Any other questions? So I guess next time, bring questions if you have them on practice problems. And then when that's done, we'll go back to the problem we were working on, calculating the normal stresses due to internal tension and internal bending moment.